Recording. Recording. Great. You made it. Okay. Of course. I'll start up here, but I might actually. Hand's giving me grief today, so we'll see, but I'll try down here. All right. So last week, we saw kind of some new age analysis techniques, right? We saw randomization, so resampling with randomization, and where we said, okay, if our null hypothesis is that there really is no difference between these two groups, I should be able to reassign these groups and get essentially the same results, right? And so from there, we developed, or we saw from our randomizations, right, that our randomizations started to look like this shape, right? A symmetric unimodal. We're going to start calling this the normal. We already have, but this is going to be called the normal distribution. And we said, okay, if I have an observation here, right, this far out on our curve, this curve is going to be centered on the population proportion, for example. Okay. And then we said, okay, if I have a sample proportion that's way out here, right, then what can we do? We can count the number of successes, or kind of the number of proportions that are more extreme than our proportion, right? From just resampling, okay, we're centered on these proportions should be the same or equal to 0.5, for example. And so now, or last week, we were able to just count how many of these samples from our 10,000 randomized samples, or 1,000, or some high number, right? We were able to count how many were more extreme, right? And from there, we spawned the p-value, okay? And so I guess I'll label this as review from last week. And so we introduced the p-value, and the p-value is going to come back into play in a big way today. And so let's remember what the definition of the p-value is. Okay? And it's going to be the same as it was last week, okay? Except we're going to start calling it the probability instead of the proportion of samples that were more extreme than what we saw. Okay? And so the p-value is the probability of seeing a statistic. So generically, a statistic, that's something like a p hat or a sample mean x bar, right? As extreme or more extreme than what we saw in our sample, assuming the null hypothesis is true, right? That was the assumption that we made last week. And we'll continue to make, assuming, I'll just do the abbreviated H naught is true. Feel like there's one too many bumps in that true. There. So what does this translate to? As extreme or more extreme? Well, that's why we counted kind of the proportions in the tail. These things can happen by random chance alone, right? But we said, okay, if this value is really, really small, then that's evidence against the proportion being centered on P, right? It's probably centered on something closer to this upper tail. We don't take it that far, right? We just say, nah, unlikely that it came from this distribution, right? That said that P is equal to some number. Okay. And so, last week we kind of used the randomization techniques to introduce the p-value, but also focusing on the null hypothesis, right? Because we do all our testing assuming that the null hypothesis is true. In terms of tests, right? So on the quiz and on the final exam, I can't make you do randomization, obviously. And so then we're going to need to rely on mathematical models, right? Kind of taking it back a little bit old school, or maybe not old school, but traditional statistics rely on mathematical models. So this is kind of new age, but we're doing the same thing with these mathematical models. We also talked about confidence intervals, and we built confidence intervals using the bootstrap, right? So where we resample from our sample, pretending that our sample is now the population, and we generate many, many samples from our sample, right? And then we were able to build confidence intervals. Today, I want to focus on the normal distribution and hypothesis testing with the p-value. Okay. I suspect there's a lot going on in chapter 13. And so it will probably run into Thursday as well. Okay. But luckily, chapter 14 is just a little shorty, okay, on decision errors. Wait, hello? Let me mute everyone. There we go. So startling. So this probability, right? Might remember I've said it just briefly, but a probability is a proportion, which is roughly a percentage, right? All these three P's can be used interchangeably, right? As long as you divide your percentage by 100, then they're all the same. Okay. And so last week we counted, okay, how many of my 10,000 samples were more extreme than what we saw just by random chance alone, right? And so now we're going to need to find a way to find this area, but without the randomization. Okay. And so I'll call that kind of the end of our review. So today, we're going to talk about the normal distribution. And so we just happened to find that this was the general shape that emerged for all our randomizations and even our bootstraps, right? And so we kind of get all these observations close to the center, and then we kind of have some that are a little bit smaller and some that are a little bit higher, but generally they follow this shape. Okay. And so the normal distribution is a name, so I'm going to capitalize it. You don't have to, right? But it's just to emphasize that it's a name, okay? Or the Gaussian distribution if you want. But I think normal is a little bit nicer. Okay, and so the normal distribution Thinking back, way back, before calculators, before computers, obviously. What a find. What a find with the normal distribution. Because what can we do? If we find that a lot of things follow this shape, okay? And so this is the shape. The shape of the distribution. This curve can be represented mathematically. We're not going to do that, okay? Because it's not fun calculus. But what can we do? If we have this distribution, we can represent it mathematically. Then if we want to find the area under the curve, areas under the curve, I don't expect you to have taken calculus 2, but that sounds like integration to me, right? And so I got one very excited person. Well, we won't get to do it. I know the normal distribution formula, and it's not fun. It is not fun. It's not fun. But we've got software now, so we don't actually have to integrate it. But to find areas under the curve, right, we would integrate this thing. Okay? And so that requires calculus, but now we use software. Okay? And I was playing around because I forgot to check it last night. But my calculator does it. Not to brag or anything, but yours probably does too. So you'll be able to find areas under the curve. Okay. Why is that so important? Because those are the probabilities. Okay. And so we will use software or a calculator to find areas under the curve. Oops. And these areas under the curve are probabilities. So the probability of seeing something, hey, that sounds familiar. The probability of seeing something as a statistic, as extreme or more extreme than what we saw. And so really what we're finding is the area under the curve. So pretty neat. Thinking about probabilities, right? Probabilities, well, they have to be between 0 and 1. Okay. And so some facts. Probabilities, right, are proportions, and proportions are between 0 and 1. And so probabilities must be between 0 and 1. If they have to be between 0 and 1, okay, then the total area under the curve must be 1, right? Thinking about all the possible outcomes. Okay. And so here you've got a stretch of outcomes. And it is hard to kind of see these things generically, but we'll see some examples. Okay. So we'll have all our possible outcomes and then the probabilities of those outcomes as the area under the curve. Okay. And so the total area under the curve is 1. Okay. but kind of mind-boggling, is that this curve never closes, in theory, never closes on the axis. Okay? And so it just keeps going and going to negative infinity and positive infinity. And so the reason I find that so mind-boggling is because the total area is still 1, right? But from negative infinity to positive infinity, okay? That's just in theory. Sometimes we'll have outcomes that can't be less than 0, for example, and things like that. But in theory, they go to negative infinity and positive infinity. Okay? And so the tails, and by the tails, I mean this little guy here, the tails never close on the axis. And continue. I'll say in theory. To plus minus infinity. How you can interpret that is anything can happen, right? And so, the probability is very, very, very small, right? Because the area under the curve is very, very, very small, right? But it can happen, or at least in theory. Right? So we allow it to happen. Okay. So if something follows a normal distribution, right, then there are two things that we need to know in order to know everything about this normal distribution. So we've got the shape, okay, and to describe a normal distribution, we need to know the center and the spread of this thing. Oh. We need to know the center and spread. Oh. Been a long time, right? But we talked about, okay, to describe a distribution, so to fully describe a distribution, we need to talk about the shape, the center, and the spread, right? And so now we have the shape, it's a normal distribution, and then we need to know the center and the spread of this thing. And I'm gonna steal, let's see here, I'm gonna steal a visual from here. Copy. I'll paste it small, but then zoom in. Rude. So here we have a normal distribution. So both of these have the same shape, right? And this first one is centered on 0. And what we said, thinking way, way back, if we have a normal distribution, then the best center or a best measure of center is the mean, right? And the best measure of spread is the standard deviation, or the most appropriate. And so here we have a standard deviation of 1. Over here, we have a different distribution with a center of 19 and a standard deviation of 4. Sorry, it's zoomed in, so my pointer is huge. These look the same, right? If I look at these and compare these look the same, right? But when we put them on the same scale, they look like this. Okay. So here's the first one, centered on 0 with a standard deviation of 1. And here's the second one centered on 19 with a standard deviation of 4, right? Nice and flattened out. Remembering that the total area is 1, right? So if you have more spread, then it kind of flattens out. And if you have very little spread, right, then everything kind of happens close to the mean, right? And so then we get this kind of nice high peak. But for us, when we'll be drawing these things, they all look the same, right? We just say what the center is and we say what the spread is, right? So just understanding that, okay, if I have more spread, it's going to look like this, allowing for what? More variability, right, in our outcomes. So here, a larger spread, right? Sigma equals 4, the standard deviation is 4. Oh, she didn't use sigma, let's use ST. Standard deviation is 4. Allows for more variability in our outcomes or observations. Okay. So when do we use this? Right, our ultimate goal is to find areas under the curve or probabilities, right? We can use Excel or a calculator or R or an online calculator. They all exist. Old school is using a Z table, right? Which leads us to the Zs, right? Z scores, which do what? They allow us to compare standardized values. Okay? And so I'll use an example. Oops. Oh, I forgot. To summarize, a normal distribution we use the following notation. X, so some capital X, which is our outcome, our outcomes or the observations, follows so this is a tilde, and you're going to read it as follows. Capital N stands for normal. Okay. Normal distribution. And to fully describe this normal distribution, we had to have the center and the spread as well, right? And so with a center equal to mu and a spread, so comma spread equal to sigma. Or more concisely, right? Center and spread, or X follows a normal distribution, mu sigma. Mu and sigma determine where this thing is centered and how much spread or how much variability we have. And we call these parameters. These are parameters not only because they're from the population, right? That is a parameter, but they're also the parameters needed for the normal distribution. For the normal distribution. Okay. So knowing these three things, right? Shape, center, spread, right? Then I can do what? I can standardize values, right? Which is usually our go-to move. Yeah. And she used to have an example of Jim and Pam, which I thought was pretty cute, but she has changed it to Nell and Cian. That's okay. That's fun construction noise. And so it begins. They took down the portable. Did you guys see that? The one with the classrooms in it. Yeah, right? Oh, they just moved it?
Yeah.
Oh. I was like, oh yeah, we don't have to teach in there anymore. Awesome. It's like always freezing or just so hot. There's nothing normal going on in there. But I got one, so that's good. Okay, so it's just closer to the C building. Oh. So in the States, for, I don't know, university entrance requirements, they write either the SATs or the ACTs, and I'm pretty sure you could write both, but they're just kind of academic aptitude tests. Okay. So SAT scores follow a nearly normal distribution, good enough for us. Okay. And so here we're going to latch on to that normal distribution because then we know the shape of this thing, right? And it opens up, okay, then we're going to be able to find probabilities associated with this thing. And so that's a nice thing to have. Okay? And kind of a sidebar, but many things follow a normal distribution, or at least a nearly normal distribution. Okay? And so that's kind of the beauty of it, and having this, this mathematical way of representing it that we don't care about, but it exists. Okay. So SAT scores follow a nearly normal distribution with a mean of 1,500 points and a standard deviation of 300 points. Okay. And so if we have SAT scores on a number line here, right? That's the outcome that we're talking about. Then we're told the shape looks like this. Now the shape that we draw is always going to look the same. You don't really change it depending on the spread or the center. But it is, I encourage you to always draw it and sketch it out to see what you need to solve for, but it's also a way for you to communicate to me how you interpreted the question and what you felt that you needed to solve for. Okay. And so with a couple more examples, obviously, then you might see, okay, that's how I communicate to me, your marker, what you thought you were supposed to do. Okay? And as long as you follow through with that, then that's okay. Right? And with practice, it'll help you solve these problems. But I know in the beginning, because I remember thinking, why do I need to draw this thing all the time? Right? And then I learned why. So just stick with it. and it'll work out. How's that? Ominous. So we're told that the mean of these SAT scores, that's going to be the center, right? The mean is at 1,500. There's no natural spot to put the standard deviation, and so I just kind of jot it down somewhere nearby because we will need it, right? I don't spend any time kind of drawing out these kind of the width or anything like that, right? We're just looking at this distribution. Great. So now, right, we can find other scores, right? Maybe you have a score of 1,800. Wow, crazy, right? I think that's good. I don't know. I need to figure out what the SATs are out of. I still don't know.
It used to be 1,600.
1,600? I feel like she scored 1,800. I think they probably, well, yeah, this might be old. Either way, we'll say it goes to infinity. Hard to get past a certain point, though. Probability gets really small. How about the ACT scores? ACT scores also follow a nearly normal distribution. Okay, so now if we imagine our ACT scores, they're on this number line. And they also follow a nearly normal distribution. Oh, that wasn't very good, was it? In here, there's a sticker, which is pretty fun, but I always forget to use it. There is a normal distribution sticker that I could be using, but makes it sound important, right? There's a sticker, pre-made sticker for it. It is. So we've got the shape, okay. With a mean of 21. Huh. Okay, that's okay. Center here at 21. And a standard deviation of 5. So sigma is 5. Oh. How do universities compare these scores? Right? They're not on the same scale. They've got different spread, right? And so one thing that we're going to do, okay, or the main thing that we're going to do is we're going to standardize scores, right? And so if we have, suppose Nell scored 1,800 points on their SATs, and so Nell, or let's start incorporating some subscript notation. So X is the observation, okay? And then you can write Nell down here. Okay. This is the observation for Nell. So the observed value for Nell was 1,800. In terms of our scores, our SAT scores, I'm going to plop that down somewhere here. Now, it doesn't actually matter where I put it. It's just for visualization. As long as you're on the correct side of the mean, right, either above or below the mean as appropriate, then it's really just to visualize the problem. Cian scored 24 points on their ACTs. I have a feeling that Cian, but I had a friend named Cian, or I guess I have a friend named Cian. She's still around, but I feel like she pronounces it weird, and maybe that's supposed to be something fancy. I'll call her cyan. So the observed value for cyan is 24. When I go to jot that down on here on my ACT scores for the scale, right, I'm also above the mean. That's good. So both of these scores are above the mean. Okay. So they're both doing well. Let's see. I'll put it kind of in the same-ish spot. Okay. Again, just to visualize. Okay. Remembering that on this line here, that's my scale. This is a number line for my outcomes. Okay. To compare these, right, what can we talk about? We can talk about the number of standard deviations above the mean they are, right? And so to compare X now and X cyan, we can calculate how many standard deviations from the mean they scored. In this case, they're both above the mean, but you're allowed to score below the mean. And so let's just talk about from the mean. From the mean, they scored. With respect to their distributions. With respect to their distributions. Otherwise, no one would write the ACTs because your scores are clearly going to be quite low compared to just kind of the raw scores of the SAT scores. And so if you had to problem solve this and figure out how many standard deviations away from 1500, 1800 is, if the standard deviation is 300, what would you end up doing? You would take the distance. So the number of standard deviations is the distance divided by sigma, right? Or the standard deviations. In fact, we're going to use x minus mu over sigma, right? Finding that distance by taking our observed value, the value that we're interested in, and subtracting the mean. Okay. By doing it kind of consistently like this, what are we going to get? If values are above the mean, then we get a positive distance, right? But if values are below the mean, then we're going to get a negative distance. And so we get information out of that positive and negative by doing it consistently, by using x minus mu, okay? Remembering that here, mu is 1500 and here mu is 21. And so here, we always calculate the distance as x minus mu. And then positive values mean you're above the mean and negative values mean you're below the mean. I'll say so positive distances I'm trying to avoid the word mean because it's also the center. I can't mean X is above the mean. Is above mu, let's say. And negative distances mean X is below the mean. Below. Yeah. Instead of talking about the number of standard deviations, that X is from the mean, number of standard deviations, X is from mu, technically is what we're calculating. We start calling these Z. And so a Z is a standardized value. Z is called a standardized value. Which kind of gives rise to Z scores, right? Okay. If X came from a normal distribution, centered on mu with a spread of sigma, then if I standardize it, all I'm really doing is I'm just shrinking it down, right? And I'm putting it on a center of what? If we think about if X is at the original center, so if X is equal to mu, then I have a distance of 0, right? And so then Z is centered on 0. Right? And as a fact, it's going to have a standard deviation of 1. So Z, or Z scores, follow a normal distribution with a center of 0 and a standard deviation of 1. Instead of center, I should say mean. Otherwise, I'm inconsistent. And a standard deviation of 1. In shorthand, we can write this. Z follows a normal distribution with a mean of 1 or mean of 0 and a standard deviation of 1. This is really the distribution that we're going to use to calculate probabilities. If you're using Excel, you don't actually need to calculate the Z, right? It just makes it a lot easier because otherwise you'd have to do all that calculus for every single distribution that you encounter, right? And so because it relies on the mean and the standard deviation, as we've seen, right, that determines the shape of this curve. Right, and so then every new mean, every new standard deviation, you would need to recalculate those areas. Whereas for Z, right, it has a fixed mean of 0 and a fixed standard deviation of 1. And so kind of way back, someone decided, you know what, I'm just gonna make a table of all these things. And so that's where the Z table came from. Right, they're just going to do all that calculus once and for all, and then be able to refer to a table. And so when I was playing around with my calculator, I encourage you to check it out and see if yours has it. Mine was in the menu. And then I see a normal distribution. Ah, enticing. Go ahead, click on it. Or you know what, maybe what I'll try to do. It's been a long time since I tried to do something weird like this. Been a long time. Aha. Okay, let's see here. Can even do it. This is my old school document camera. Wait, okay. It's upside down. The heck? How about now? There-ish. It keeps wanting to scan it. Oh. Okay, so when I go in here, I see this beautiful normal distribution here. Gives me some options, right? And for now, right, I like seeing all that normal there. It gives me the normal probability distribution, the normal cumulative distribution, the inverse normal, right? And so these are all worth exploring. And so I'll just click on one. These are all the components that we were just talking about, isn't it? And so it needs an X, it needs a sigma, and it needs a mu, and I think doesn't need anything else. Let's see here. Yes. For me, I hit menu. How about setup? Because mine's just an older version of your guys', I think. We don't need it. It's just fun to have, right? And so, oh, got it?
Okay. I found a feature. I don't know what it does.
That's okay. We haven't got there yet. But so somewhere in many calculators, any kind of scientific calculator, I think, will have access to this. And so we just need to know what's it gonna do. What you gonna do when you live in a shoe? Okay. But pretty fun. It just eliminates the need to use Excel eventually. Okay. And so that's nice. Where was I? So the Z distribution, we know the shape, right? We've got our Z scores here. Has to be centered on 0, and the standard deviation is 1. So Z, right, tells us how many standard deviations from the mean we are. Z equals x minus mu over sigma. A Z score tells us how many standard deviations, so sigma, an observation X is from the mean, which is your mu. Like we saw, right? We already said that, okay, if I'm above the mean, then I get positive distances, which is going to be reflected in the Z, because, I'll do it here, X minus mu is either positive or negative, right? Reflecting if you're above or below the mean. Sigma has to be positive. You can't have a negative spread, right? And so sigma is always positive. And so I'll say, since sigma is always positive, Z will be positive if the X is above the mean, and Z will be negative if X is below the mean. Z will be positive if X is above the mean, and Z will be negative if X is below the mean. Oh. Because if it's centered on 0, then I have positive values up here, and I can just as likely have negative values down here. So the positive and the negative in the Z score, right, also communicates not just how many standard deviations away from the mean you are, but whether it's above or below. So for example, Z equal to negative 1.7, right, means X is 1.7 standard deviations below the mean.
Calculator function for the p-values.
Yeah.
We just use that the other one is the smallest p-value is mapping it and that's
Totally. We're building up to that. But exactly. Right. So from the Z, we need to calculate Z first, but then we'll be able to find probabilities. Some you can often bypass the Z. Right. Yeah, you can feed it your mean and your standard deviation, and in the background, it'll calculate your Z likely, right? It's not going to do the approximation every time, but so it'll just do it for you, right? And so, but Z is kind of a nice thing to have a good handle on, just because it is a standardized value, right? And you're able to compare them. But yeah, quickly becoming obsolete. You don't really need it. And so, all right, let's see here. But we do use it to compare values, bringing us back to Nell and Cian. Who scored better? Right? And so we can calculate a Z score for Nell, and we can calculate a Z score for Cian. Right? And I'm gonna cheat and just copy this down so I don't have to remember it all. Oh, let's do that here. To compare scores, we can compare the Z scores. And so usually what we do if we're comparing values from two different distributions, we use these little subscripts again, right? And so I'm going to find a Z for now, which is going to be the score for now. Whoops, maybe capitalize that name. Minus the mean of the scores that she came from, the SAT scores, over sigma. So her score was 1800 minus mu, which was 1500 divided by 300, which is hopefully 1. Wait, leave nothing to chance. I'll do some decimal places just for completeness. Oops. So Nell scored 1 standard deviation above the mean for the SAT scores. And I'll do them side by side here. Do the same thing for Cian. And so I have my score for Cian minus the mean of the ACT scores, because that's where the score came from, over sigma. And Cian scored, oh, I have it here, 24. And the mean is 21 divided by the standard deviation, which is 5. 24 minus 21 is 3 divided by 5. I get a Z of 0.6. Old habits, usually, because the Z table, old school, goes to 2 decimal places. Typically, we do Z to 2 decimal places, but that's just me being picky and old. Okay. So Cian scored 0.6 standard deviations above her mean, right? And Nell scored 1 standard deviation above her mean. And so this is the better score. Right? This is higher than Nell's score is better than Cian's. Right. So the university is looking at these scores, and they would choose Nell over Cian just based off of these scores. Right. And so that's how you're able to write the 2 different entrance exams. So you can compare.
Such complicated thing rather than just convert it into percentage.
Yeah, that's what you do. That's all I did originally. It's a lot of work for something that's like super intuitive.
Do you mean the percentage? Like, oh, yeah. Oh, like the total? Because, yeah, it helps to know what they max out at. But even if we did know that, then with this spread, I the wed, if the spread, oh, I need my pointer, depending on the spread, right, then maybe it's harder to get 95% on the ACTs versus 95% on the SATs, right? And so that's why we need to take so the percentages, yes, of course, you can just compare the percentages, and generally they'll be about the same, right? You don't expect a ton of different spread, but you do need to take the spread into account because it's possible that hardly anyone gets over 90% on the ACTs, right? It's potentially, I'm just making this up, but it's potentially a harder exam just in general, right? And so you're expecting lower scores, right? But still good in comparison to the SATs potentially, right? And so, yeah, of course, you can just look at the percentages and compare them straight across, but you are ignoring the spread, right, in doing that. And that's why. Okay. So what if we built this out, right? And we said, okay, one standard deviation above the mean. What's the probability of, or what proportion of writers, right, scored higher than now? And so from a Z-score, we can calculate, right, what proportion of test writers we can calculate. And maybe instead of proportion, I'll say the probability a test writer scores better than now, for example. So if we know all SAT scores look like this, centered on 1500 with a standard deviation of 300, and we have our, I keep not capitalizing that name. We saw a score of 1800. If we want to find the probability, right, then we remember, okay, a probability is an area under the curve. And so the area under the curve, if we draw a line here, we can find the probability that someone scores lower than now, right? And we can find the probability that someone scores higher than now. And so here, if we want to find the probability that a test writer scores better than now, then the area that we want is going to be this area. And usually put a little question mark there just to indicate that that's what I'm looking for. Most software, you can specify in Excel if you want the upper tail, but most software, and I'm pretty sure the calculator as well, will give you the area to the left. The Z table, if you've seen the Z table, gives you the area to the left, and your calculator is going to give you the area to the left, and why does it only need to give you the area to the left? The area to the left being this area here. Because we can leverage the fact that the total area is 1, right? So the total area, the total probability of all possible scores is 1, right? And so now, right, if I know the total area to the left is 0.7, right, then I also know that the total area to the right is 0.3, 1 minus 0.7. And so most software or calculators only give the area to the left of a z of x or z. But to find the area to the right, right? But to find the area to the right, we leverage the fact that the total area is 1. We leverage the fact that the total area is 1, which means that the area to the right is 1 minus the area to the left. Eventually, we'll build up to kind of building, using these as puzzle pieces, right? And we can kind of chop off any area that we want from 1, or sorry, that we don't want, right? And we can move around. So one kind of easy way of avoiding software and avoiding calculators and calculus and all that fun stuff is using the empirical rule. So one way to approximate areas under the curve is using the empirical rule. Or what's called the 68, 95, 99.7 rule. Rolls off your tongue. 68, 95, 99.7% rule. Okay. What's in a name? Well, everything. The 68, 95, 99.7 rule says that if you have a normal distribution, then 68% of the curve is captured between the first standard deviation or within 1 standard deviation from the mean. So the 68, 95, 99.7% rule says 68% of the normal or of unnormal distribution, I should say, is captured And with that captured, you might be having flashbacks to confidence intervals. And yes, they are related, of course. And so 68% of the normal distribution is captured within one standard deviation of the mean. Right? Or kind of more simply, a Z of plus minus 1. Or Z equal to plus minus 1. So it does require a normal distribution. The problem with the normal distribution, if we kind of take a step back and we had a rectangle, it's easy to find the area under the curve, right, of a rectangle, right? We know how to do that, right? Find the area of a square, a rectangle, like length times the width, right? Or the height times the width, I guess. Now we've got this darn curve, right? Making it difficult. Okay? And so that's why we need these little tricks. Okay. But if we talk about Z we know is centered on with a mean of 0. We also know Z has a standard deviation of 1. Okay. So what it's saying is that if you go down to Z equals -1 and up to Z equals +1, right? Move out one standard deviation, okay? Because the standard deviation for Z is 1, right? Then the area here, and maybe I'll do this in pink instead. This area is 68% or 0.68. It's important that it's within these, so symmetric around the mean, right? I've moved down one standard deviation and up one standard deviation. And then I've captured the central 0.68 of this curve. It's symmetric. So how much is left over? 1 minus 0.68 is left over. And so here, therefore, 1 minus 0.68 is left over. 1 minus 0.68. And maybe I'll do that math here, 0.32 is left over. Let me clean that up. And that has to be split evenly amongst the tails, right? Because it's symmetric. Which must be split evenly between the tails. .32 divided by 2 puts me at 0.16. So then this is 0.32 divided by 2, which is 0.16. And this is 0.32 divided by 2, which is 0.16. So knowing that you're within one standard deviation, right? The probability of scoring higher, right, than Nell, who is one standard deviation above the mean, is 16%. So 16% of test takers are expected to score higher than Nell did, right? Whether that's good or bad, I don't know. Yeah. But a lot of kind of academic exams, like the actuarial exams, for example, every every test session, because they run them kind of 3 times a year, I think it is, you have to score in the top 5%, right? Which could fluctuate depending on who you wrote against, right? The mean and the standard deviation changes depending on who you went up against, right? And so in order to pass, you have to be in the top 5%, I think it is, or 10% or something. But so this is a nice way to approximate areas under the curve. 68% was within 1 standard deviation, right? If you had to guess what the 95% is, could it possibly be 2? It is, right? And so then let's keep going. 95% of a normal distribution is captured within 2 standard deviations of the mean. Or Z is plus minus 2. And maybe I'll put this on its own page. Which means that again, we have Z scores centered on 0, standard deviation of 1. So now I bypass -1 and 1. And I'm going to jump to -2 and 2. Because now I've moved out 2 standard deviations, or a Z score of plus minus 2. And that's where the Z scores are going to come into play still, right? Because we can still approximate areas under the curve without software. So here should be symmetric, but we have 95% or 0.95, right? Probabilities are proportions. So what's the area in the tail then? If I have 95% in the middle, by symmetry, I have 5% left over, split evenly amongst the tails. And so now, and usually how I denote this, because it can get pretty messy if we're shading things in and there's overlap and things like that. So I just kind of draw an arrow up and over to indicate that this area is 0.05 divided by 2, which is 0.025. Right. So 1 minus 0.95 is 0.05 split between the tails. So, yeah, 1800 plus 300. Yeah. And so same thing here, 0.025. So the probability, right, of scoring higher than 2 standard deviations above the mean is 2.5%, very small. Right? And so you'd probably get accepted, right? Because that's hard to do. What if there was a score of 1.8 standard deviations above the mean? What's the probability of scoring there? We can use software to find the exact probability, right? Or we can approximate the probability. Right? This is kind of a sidebar example. We can approximate the probability of scoring 1.7 standard deviations above the mean. We had our cutoff at 1 and 2, and we have a score of 1.7. But from earlier, we found that the probability of scoring more than 2 standard deviations, clean that up, was 0.025. And the probability of scoring more than 1 standard deviation was 0.16. So then all we can say about that probability is that it's somewhere between 0.025 and 0.16. Well, that's all we know so far. The probability is between 0.025 and 0.16. We need to use software, right, to get a more precise estimate. But it is an approximation. It's just not very good. And we can use software or your calculator to find the exact probability. Already, huh? I got so much to say. Means I'm running out of time. So most people aren't pleased with that approximation, somewhere between 0.025 or 2.5% and 16%, right? But it is how we can use the 6895 99.7 rule. What do you think the 99.7 is? Probably 3 standard deviations away, right? And so I'll use the same format here. 99.7%. Why don't we round that up to 100? Because then we'd have to go to negative infinity and positive infinity. We don't want to do that, right? But 99.7% of the normal distribution let's see, how did I phrase it, is captured within 3 standard deviations, or z equal to plus minus 3. Now we're getting somewhere. Right? Z is centered on 0 still, and sigma is 1. And I've moved -1, -2, -3, up 1, up 2, up 3. Just to visualize. Then between -3 and +3, I've got the central 99.7% or 0.997. Which means 1 minus 0.997, which is very, very small. Scientific notation. I wanted the decimals. Okay. 1, 2, 3, 3. Okay. Is split evenly between the tails, right? By symmetry. Is split between the tails. So this becomes very, very small. 0.003 divided by 2. Get 0.0015. 1, 2, 3. And same thing on the other end. Very, very small. Right? Which means what? The probability of scoring more than 3 standard deviations above the mean is very, very, very small, right? And so if you find that your statistic, right, is more than 3 standard deviations above the mean, then that's unlikely, right? It's more likely that it came from a distribution centered on something else. Right? And so that's how we're going to use it. But we need to kind of get familiar with finding the areas under the curves and things like that. And let's see here. In your calculator, I'm going to try the normal PD and say 1800. I didn't play around with it. So we'll see what happens. Oh, I gave it the sigma, which was 300, and the mean was 1500. I think I want the CDF. Anyways, I'll have to play around with that. Sorry, to tell you which one to use. I'll need to get my mitts on one of the new ones so I can look and see what that one looks like too. Buy a calculator, but I have a bag of calculators. Maybe I have one in there. So then the 68, 95, 99.7 rule gives us just a quick approximation of areas under the curve, right? And so if we find that we're 2.5 standard deviations above the mean, right? Then what do we know? The probability of being 2.5 standard deviations above the mean is somewhere between 0.0015 and 0.025, very small still, right? And so we can break this up and use it as a puzzle piece, or a puzzle, I should say. And brings me to the sticker. The sticker has 1 standard deviation, 2 standard deviations, and then I think they ditched the 3 standard deviations because it's so far into the tails. All right. And so usually we just have the 1 and the 2, but I make room and I draw all 3. If you are in any sort of business setting, you'll probably hear about Lean Six Sigma, which is a process that they use, but really all it's referring to is you've captured all of the curve essentially within a total of 6 sigma or 6 standard deviations, right? And so just something to know. And this is true for all normal distributions, right? For any normal distribution, you have captured the central 99.7% of the curve within 3 standard deviations. So it's possible to go beyond 3, right? but it's very unlikely. Okay. I'll remove this sticker because I draw my own bad looking ones. So here, I'll do it for both past 3. It is possible for Z to go to plus minus infinity. Okay. But the probability is 0.0015 in either direction, right? And so it's very unlikely. But the probability is 0.0015 in either direction. Making it very unlikely. Oops. Making it very unlikely. So it's possible, but unlikely. Well, I always struggle drawing the 68, 95, 99.7 rule all on the same graph. Okay, but we can put it all together. Centered on 0, Z has a standard deviation of 1, -1, -2, -3, 1, 2, 3. To simplify things, I'm going to focus on the areas in the tails, because that's what we calculated, but we also know that those are going to be our p-values, right? And so later, right, the probability of seeing something as extreme or more extreme, if I'm on the lower end, then more extreme is into the lower tail. If I'm on the upper end, more extreme is into the upper tail, right? So it depends on what your Z-score is. But more extreme just means area in the tail. And so that's why I'm going to focus on the area in the tail. Let's see here. I'll use orange for the 3s. .0015. I'll use green for the 2s. 0.025. .025. Wonky, but that's okay. It's just to visualize. And try not to use pink, I'll use purple. 0.16. 0.16. Trying to decide, where's my Excel here? I just want a new one. Or an old one, I guess. I'll just start a new tab. If I tell Excel, where's my equal sign? Equals norm. We're going to use norm.s.dist. Norm.dist is older. Okay. norm.s.dist, I can give it a z, and let's give it a z of 1, right? 1 standard deviation above the mean. Okay. And then it wants to know cumulative. It's either true or false. For z-scores, cumulative just means up to and including that point, right? Is the final exam cumulative? It just means all the things up to the final exam, right? And so we're always going to say true. The cumulative is false is for discrete distributions, which we're not going to deal with here. And so for us, it's always true. You always want the area up to and including that point. Okay. On a continuous scale, if you said false, you'd be asking it to find the area with a width of 0, and it should give you 0. I think it's going to give you something because it bumps it out just a smidge on either side, pretends that there's a little bit of area there, but we're going to use cumulative equals true. Oops. No. Go. Do the thing. Shift. No. Return. There. 0.841345. What is that? That's going to be the area to the left, right? Just like we said, okay, a lot of software is going to give us the area to the left. How about I do the same thing and I find equals norm dot s dot dist of -1, right? Just to confirm the 68 aspect of the 68, 95, 99.7 rule. Cumulative equals true. Where's my, and, oh. There. I don't know about you, but 0.158655 looks a lot like 0.16. Right? And so what can we do to confirm the 68 in the center? Well, if both of these are areas to the left, then the area between them must be, let's see here, equal to this guy minus, where's my minus? This guy. 0.682689, roughly 68%. And so, of course, the exact areas can be done, but the 68, 95, 99.7 rule gives us enough to work off of. Let's see here. I'll do this one. Screenshot this. Whoops. And bring it in. No, I want the pictures now. Crop. This is referring to this cell, of course, because it's highlighted. And we're going to look at this norm.s.dist of 1 and true. Need to give myself just a little bit of room. A normal distribution, we gave it z equals 1 and cumulative equals true. To get the probability up to and including z equals 1. To get the probability up to and including z equals 1. Usually in a normal distribution, so on a continuous scale, you don't need to worry about z being less than 1 and greater than 1. You can just kind of pick it up at 1, okay, because the area at any singular point is 0, right? And so, because there's no width, right? And so by that, we can say, okay, this gives us z centered on 0 at 1. It tells us that this area is 0.841345. All the area to the left. Okay? Because it's up to and including z equals 1. But also, that means the probability or the area above 1 is going to be 1 minus 0.841345. So you don't need to make that adjustment of, okay, well, one of them uses 1 and one of them doesn't. We ignore that. Okay? And so we have 1 minus 0.841345. Which should be the same as this, which was norm dot s dot dist of -1 and true. Which is 0.158655. Should be the same by symmetry. This, let's see here, what color haven't I used? Purple again. This is A1 minus A2. The probability of being within plus minus 1. Probability of being within plus minus z equal to plus minus 1. Oops. I'll clean that up. But roughly 68%, right? And roughly 0.16 in the tails, right? 0.158655. And when you play around with your calculator, I'm pretty sure that it's going to want the normal CD, which is the cumulative distribution, okay, which is kind of referring to this up to and including this point. Okay. Let's see here. I wonder if my, it wants, let's say, the lower value and the upper value. It's trying to do something fancy to integrate. But then it wants, so let's see here. If I force my lower to be -1, my upper to be +1, my sigma to be 1, and my mu to be 0. Let's try that. Ta-da! So I can force my mu and sigma to be a z distribution. because we're talking about Zs here. But you could bypass that and give it the mu and the sigma, and then you don't need the Zs, but it'll do the same thing.
How do you do that? Only want to pick one side that you're 1.7.
I haven't mucked around with it, but I'd probably, yeah, do something, like what if you did it, what if you made the lower, so let's say we want to confirm this value. What if you made the lower negative 99 or something, right? Just kind of push the lower limit. Negative 99, let's see if it complains. I get 0.841345, close enough. So then if you want to open it up and find this total area, then you can change the lower to like negative 99 or something like that. To kind of, I used a mu of 0 and a sigma of 1 because that's what Z has. Right? But it doesn't. There you go. Nice. So
So for example, you use the negative 1.7, 1.7.
yep.
Get 0.91 inside.
This one. So then let's try, I'm gonna set it up. Let's see here. No, now I've done it. Whoa, don't get seasick. Oh no, how did I do it so well before? Oh. Whoa. Old school. Okay. So if I do my normal CD, it wants my lower value. And what we could do is we could set the lower value to be 1.7. Oh no, because it gives the area to the left anyways. So let's just make it, oops, sorry, negative 99. And then enter. And then the upper, I'm gonna make it 1.7. And because this is a Z, sigma is 1, and the standard deviation is, or the mean is 0, I get this. 0.95. There. Okay. Now I'm gonna take this. No. How do I get back out of here? Cancel. Okay. So for our example, Z is centered on 0 and sigma is 1, and we had a 1.7. And our calculator is telling us that the area to the left is 0.955 4345372, which means that this is going to be 1 minus 0.955 4345372. Might be nice to store this. I wonder if I can store it to A. Okay. Get out of that. 1 minus A I get 0.044565. 6278. Which is between 0.025 and 0.16, but now we have the actual value. Wow, you guys really let me go overtime. Sorry. If you have any questions, let me know. Otherwise, we'll keep working on the normal distribution and probabilities next day. This